In a cross-section of the axon membrane, we see the movement of sodium ions, shown as yellow spheres, into the cell as the action potential travels down the axon. As the action potential moves along the axon, brief changes in voltage across the membrane cause sodium channels, which are embedded in the axon, to open. Positive charge sodium ions then move from the outside to the inside of the cell. The positive sodium ions move inside the cell because they are attracted by its negative charge. After the action potential passes, the sodium channels close. During the resting potential, sodium ions which carry a positive charge and are represented here as yellow spheres are found mostly on the outside of the axon. Potassium ions, which also carry a positive charge and are shown here in green, are located mostly on the inside of the neuron. Large negative charge protein molecules are always found inside the cell. Other ions are present, but we will focus on the behavior of these three molecules. There are more negative charge protein molecules inside the cell than positive charge potassium ions. The inside of the cell, therefore, is more negative than the outside during the resting potential. This changes with the arrival of the action potential. Changes in voltage brought about by the arrival of the action potential cause the sodium channels to open, allowing sodium ions to enter the cell, which briefly depolarizes the axon. When an action potential reaches the axon terminals, neurotransmitter molecules are released. This is a representation of a cholinergic synapse. Cholinergic synapses use the neurotransmitter acetylcholine, which is abbreviated as ACH. In this cross-section of a synapse, we can see the three components of a typical synapse. They are the axon terminal, the synaptic cleft, and the receiving or postsynaptic cell. Within the axon terminal are many tiny packets, called synaptic vesicles, that store and release the neurotransmitter. On the receiving or postsynaptic cell are receptor molecules. In a cholinergic synapse, an action potential causes the release of ACH, which crosses the cleft and attaches to binding sites on the surface of the receptor molecules. The receptors open, allowing sodium ions to enter the postsynaptic cell, causing postsynaptic potentials. ACH molecules are inactivated by the molecule acetylcholinesterase, which is abbreviated as ACHE.
Whether a neuron fires depends on the sum of its inputs. Spatial summation is occurring in the neuron on the left. On the right, we see temporal summation. When an action potential reaches the terminal, the synaptic vesicles move to the membrane and release their transmitter into the cleft. At an excitatory synapse, this causes a slight depolarization of the postsynaptic membrane. Some neurotransmitters are transported to the terminal from the cell body. Others are formed in the terminal. Here, the precursor for the transmitter is delivered by microtubules. An enzyme in the terminal converts it into the neurotransmitter. The transmitter molecules are packaged in vesicles. When an action potential arrives at the terminal, calcium ions enter the terminal. This causes the vesicles to move to the membrane and release their transmitter into the cleft. The neurotransmitter molecules mate with receptors on the postsynaptic membrane in a lock and key fashion. Excess transmitter is removed by reuptake. On the postsynaptic membrane, sodium channels open. Finally, sodium ions enter, depolarizing the membrane.
In a cholinergic synapse, an action potential causes the release of ACH, which crosses the cleft and attaches to binding sites on the surface of the receptor molecules. In the case of the neurotransmitter ACH, the receptors open, allowing sodium ions to enter the cell, where they cause postsynaptic potentials. They are then inactivated or broken down by acetylcholinesterase. Some drugs affect behavior by inhibiting the inactivation of neurotransmitters. The neurotransmitters bind to receptor sites over and over, producing more postsynaptic potentials than normal. In the case of ACH, nerve gases and other drugs prevent ACHE from breaking down or inactivating ACH. These drugs are called acetylcholinesterase inhibitors, abbreviated as ACHEI. ACH, therefore, continues to activate receptors for longer than normal. In some cases, this can be clinically useful. In other cases, such as the use of nerve gases, the effects are often deadly. ACH molecules are inactivated by the molecule acetylcholinesterase, which is abbreviated as ACHE.